Hello, and welcome to any combo lords joining me here today. We are once again in my room due to there being some rain outside. Not enough rain to flood the combo classroom this time, but still enough that it would cause a bit of chaos on my camera, probably. So, what we are going to do today is discuss some numeral bases partially related to a Pandigital episode I dropped on my main channel, which is linked in this description. So, if anybody wants to make sure you're in tune with the later parts of this stream, you might want to watch that first, or you can watch it after this stream. I won't spoil the crucial parts. But in any case, that episode, among many of my episodes, related to having different bases counted. And it's a theme in combo class in general to think about things in other alternate ways, and another theme to play with numbers. So if you're thinking about things in alternate, unconventional ways and playing with numbers, one of the key things to think is maybe we could have counted or written our numbers differently, which will affect certain traits that we discuss here. Not all of the traits. We can in fact categorize some traits as base independent, meaning that they exist even if you were counting numbers on a pile of rocks, however you wrote those numbers. For example, something's prime factorization for a whole number, which primes make it up, is something that's base independent. No matter how I decide to write these numbers, some of them are going to be primes, others of them are going to be composites that have unique prime factorizations. A lot of the other traits that relate to divisibility might also be something that doesn't matter what base you're in. But if you see divisibility related to something like a digit sum, then suddenly we're in base dependent territory. Because when you hear the word digit, it gives you a clue that that would be different if I wrote the digits a different way. And so traits that relate to what digits a number has, or what those digits add up to, or what their collection includes, can be fun. But you may first, it's sort of like one of those joke memes where there's a curve and like the really dumb person and the really smart person came to the same conclusion, and the middle person was came to a different frustrated conclusion. And this lower conclusion and upper conclusion might be, if you don't know much about numbers, oh, it might be really cool that this thing is divisible by its digits or something. If you know a medium amount about numbers, it might be like, oh, well, that's not as cool because that relies on the system we count in. But if you look at a ton of stuff about numbers, it might go back to being like, that's interesting, because you can compare the traits to other ways we could have written the numbers and see ways that certain traits maintain themselves over many or even infinite ways we could write numbers. And of course, we could get super abstract and write numbers in a completely different way. There's no end to the possibilities. And if we encountered some alien, there's a good chance they would count in a very significantly different way that might not be a positional numeral base, where most of the bases that we've played around with, even the strange ones, have this trait called a positional numeral base, where you're putting the same set of digits in different positions, and the different positions have different values. So, and within that, a lot of the ones we've done, pretty much all the ones we've done so far, even have those values just be powers of a certain number. But within those tweaks, we can find a lot of crazy stuff, and it is one of the logical ways to construct numbers, so it's not impossible to imagine that there could be another alien that counted in another positional numeral base. And if there was, they probably wouldn't have settled on base 10 unless they happened to have some important 10-like trait about their body, like how we decided the 10 fingers was the important thing about counting, as opposed to something like the finger joints that come in threes that we could have, and some societies have counted on instead. And so if an alien was, say, counting in a different one of these bases, maybe they have their own Pandigital numbers that contain every digit. Maybe they have their own hyperelevens, or what could be called generalized repunits, that are only the digit 1. Maybe they have their own numbers that look round. A round number is a name for when you have a bunch of zeros at the end. And so on. So what traits do things like that have over the course of many bases? And are there some numbers that have traits that happen in every base, or traits that happen in more or less bases than the average number would? Well, yeah, there's a lot to investigate there. And we'll start with a few families of number that we've looked at in the past. And let me also take a peek at the comments real quick before I jump down many rabbit holes of things I want to talk about and share. Thank you to everyone who's joining me, and whoever has to go and watch this later, that's all good. I'll even add timestamps later of the chapters, so people who can only watch part of it later can see what other parts they want to catch up on. And all of you are awesome. Thanks for joining this. What we're going to first start with is one of the most obvious ones, which is what numbers would be round, as you might say, in a given base, which is a term for the numbers that, usually applied to our base, have a bunch of zeros on the end. And it doesn't have to mean something like 1,000. 2,000 could be considered still more round than like 2135 or something. And the numbers are, we could categorize how supposedly round they are based on how many zeros they have at the end, which in our base, of course, means how many powers of 10 are included in them. And what that really means in our base is that the prime factorization of the number has that many 2's as well as that many 5's. So, for example, the number 10 is the first number in our base with any 0 at the end, not counting 0 itself. And that's because it has a 2 and a 5 in it. 100, the first number with 2 zeros, or any number with 2 zeros at the end, has amongst its prime factorization at least 2 2's and at least 2 5's. Now in other bases, it's just going to mean it's round based on having multiples of the base number. And if you go down to prime factorization, you could say whatever primes make up the base number. So in binary, for example, a 0 just means it has a 2 in its prime factorization. 2 zeros means it has 2 2's in its prime factorization, and so on. In base 3, we would say, oh, these numbers, 10 and 20, have a 0 at the end because their amount, which we will often look back at the base 10, bolded one here just for a reference point for you to understand. Their amount is 4 of a thing or 8 of a thing. Oh, no, that was base 4. The base 3 ones, their amount is 3 of a thing or 6 of a thing for 20. That's because those are multiples of 3. Oh, and here, look, you get 2 zeros at the end because we're at 9, which is 2 times a 3 is in its prime factorization. So the round numbers are pretty clear. They're how many times the base number is a multiple in there. But what about the numbers that aren't like 1, 0, 0, 0, 0? The numbers that are only ones, that some would call a generalized rep unit, I like to call a hypereleven. Those numbers, we could say, have 1, 1, then 1 of the base number, and then 1 of the base number squared, and then 1 more of the base number squared, and so on. So, like, basically the number 1111 interpreted in different bases is going to be numbers that can be the result of 1 plus the b number plus the b number squared plus the b number cubed, which these have 1 as a coefficient, but we don't need to write the 1. And for example, in base 10, if I plug in 10 in there, I get the number that we write like that. But if I plug in 2 in there, I get 8 plus 4 plus 2 plus 1 is 15. And that is how binary writes 15. Now, with the hyperelevens, although they have a formula, and they in fact have other formulas, here on the OEIS, where they have some cool tables we'll look at, we can see the generalized rep unit numbers. Their formula can be simplified to this, to b to the n minus 1 over b minus 1 for a base number b. And although they have some simple formulas we could write them in, they have a lot of cool patterns and mysteries. The ones that are primes are very investigated. There's a lot of sequences noted down, like if you go on Wikipedia for rep unit, they talk all about hyper11 primes in different bases. And that's partially because the prime ones in base 2 include the biggest primes ever discovered. So 9 out of the 10 biggest primes ever discovered, and the top 8. So include some of the biggest primes of all time that we've discovered are hyperelevens in binary. Now in this list, they're showing us, converted to how base 10 would write them, which numbers are a hypereleven in that base. Now, first you get 1 after they put 0 also, because 0 technically fulfills the formula, though it doesn't count for our definition. 1 is 1 in any base here. And this column is 1 more than the base number, because that's the 11 in any base. The number that the base would write, 1, 1, comes out to 1 more than the base number. Then the third or fourth, if you count the 0 number here, is what 1, 1, 1 would mean in these bases. We can see base 2 has 1, 1, 1 at 7, base 3 has 1, 1, 1 at 13. And going back to the table, we can see that's true. 7, we write 1, 1, 1 in binary. 13, we write 1, 1, 1 in base 2. Now, one question you might have is, are there any numbers that show up on multiple of these lists, not counting the sort of a trivial 11 one? Are there any that are the third term, not counting the 0 or further, that show up on multiple lists? And like I have mentioned before, it is conjectured but not proven that there are only 2 numbers of that sort. The numbers include 31, which 31 we can see is, which term is that? Is 1, 1, 1, 1, 1 in binary. And we can see 31 is also 1, 1, 1 in base 5. Now let's see that on the table of bases. If we go down to 31 here, it has 1, 1, 1 there, and 1, 1, 1, 1, 1 there. And if we look up the conjecture real quick, we can see that it's written in terms of that generalized equation. They're saying the only non-trivial solutions to this are 31 and 8,191. And we can see that it also may be expressed as saying that 31 and 8,191 are the only 2 numbers that are rep units with at least 3 digits in 2 different bases. And this wouldn't show up in our chart there because they didn't include base 90. But that's the other one. Hasn't been proven yet, but it's a very interesting question, and it is conjectured because they've tested many numbers and they have some reasons to think it could be true that amidst the infinity no others line up in this way. But staring into infinity, sometimes you can prove things and sometimes it's hard. So back to the table of bases. There are many other open questions about these hyperelevens. Some of the main ones being, like I said, are numbers that in how many bases or multiple, and which ones are prime numbers. And you could find other interesting traits, of course, to investigate, like I have and like I will, because these hyperelevens keep showing up in all sorts of different episode topics, even when I don't plan for them to. And the other topic we could talk about number-wise here is pandigital numbers. Pandigital numbers are the topic that is in my newest episode on my main channel. And without spoiling the end thesis of that, because this will cover some other topics here, pandigital numbers contained every digit in the base at least once. And here on Wikipedia, they have a table of the smallest possible pandigital number in a given base translated into base 10. Now we can see that in binary 1, 0 fulfills the conditions, and that's 2. In base 3, 1, 0, 2 is the smallest, which we would say is the number 11. And then 75 is the next one. So this is an interesting sequence here. And we also could look at all sorts of traits of which numbers can be pandigital and line up with a certain property. And we covered many interesting properties in the first maybe third of the episode on my main channel, where we just looked like in base 10, here are some interesting numbers and some traits they can have. One trait to note was I mentioned something called persistence, where pandigital numbers can generate new pandigital numbers with their multiples, where twice the number is still pandigital in the base, 3 times the number is pandigital in the base. And it's been proven that in base 10, you can have persistent numbers of an arbitrarily large persistence. So you could have like a million persistent number that its first million multiples are pandigital. But you can't have an infinity persistent number, because that would mean that you never will hit a multiple of that's not pandigital. So strangely enough, you can have numbers that their first 1 trillion multiples, or any number you pick, are pandigital, but eventually on their way to infinity will hit a non-pandigital. However, a comment pointed out, in base 2, maybe that's not the case, and it took me a second to realize, but yeah, maybe in base 2, when you have numbers like this number should be infinity persistent. Because if I multiply it by 2, I'll still have a 0 at the end, and no matter what I multiply it by, it will be a multiple of 2, and it will keep a 0 at the end, and it will also have a 1, because it's not just the number 0. So, I believe that comment may have been right, that in binary you could have infinity persistent numbers, even though that was proven impossible in base 10. Makes me suspect that base 3 would follow the same property as base 10, but I haven't looked into it yet. So if anyone looks into persistence, which we will call pandigital persistence around here, because there is other types of persistence, like ones called additive and multiplicative persistence will show up in a future episode, so we'll call this pandigital persistence. If anyone looks into how other bases behave with that, let me know. Other things that any people could look into that I'm interested in is, could we classify highly pandigital numbers, sort of like we classify highly composite numbers, meaning on our table of bases, if I look at the number 2, that's sort of the first non-trivially pandigital number. We're going to say it needs to have multiple digits for this particular part. Let's say it needs multiple digits and needs to have all the digits in the base. So we're not including what they put all these ones here, you know. So in base 2, that's pandigital, but we're not going to count the single digit ones here. In base 3, of course it is again, because they all will be 1-0 in some base. But when we get up to 4, that's pandigital in, well, no, that's only, let's see. It's only well, no, let's see. 3 isn't pandigital in any, actually. This is just a trait. It's not in the episode that I was looking at today. 3 would need a 2 in these, in base 3, or it would need a 0 there. So 3 is actually pandigital in less than 2. If we're not counting the infinite amount of single-digit ones. 4 is back to being pandigital in binary, but not these. 5 is also pandigital in binary, but not these. where are our first numbers that are pandigital in multiple bases? For example, here, 11 was pandigital in base 3 as well as base 2. I guess we'll have to refer to this list and see that possibly 75, it'll take that to be pandigital in base 4. We'd have to check if 75 is pandigital in the others as well. 75 is pandigital in binary base 3 and base 4. We don't have the guarantee just from this list that these are pandigital in all the bases leading up to that base. So that's something I was curious about if any programmers want to mess around with. Could we classify a series of highly pandigital numbers? May have been looked into before. I haven't looked into it much yet online, but just a question that popped into my head today. Could we make highly pandigital number lists of numbers that are pandigital with multiple digits in the most amount of bases for any number up to their size? And let me plug this in. My computer is getting low. Got to keep the stream alive. Now, I'm going to take a peek to look at the comments again, and then we're going to move on to... Those are some ideas first about things that a number trait could have if we're looking for, like, am I pandigital? Am I hypereleven? Am I this round type of number? And as you will see in my full episode on my main channel, or for those who have already seen that, which is linked in the description here, the pandigitals actually, in a way, have a certain type of extra importance that these others don't have in terms of how sort of fundamental they are on the number line of any base. So the pandigitals, I've learned, have extra rare, a large presence, but all of those are fun types of numbers that will come back in future episodes. You also could investigate palindromic numbers, which numbers are palindromic in different bases or look mirrored, like 121 or 12321 or 52125 or whatever. So those are fun as well. And now I'm going to take a little peek at the comments before we switch over to another idea. Instead of looking at number traits that line up with different bases, we're going to look at particular numbers. Well, actually, it's going to be another number trait first, but it's going to lead to a few numbers that have a special property in every base. So, thank you all for joining me here. People wonder, what's this math for? Well, it's for, you never know, it's for setting up in the future of mathematics and thinking in general. You need to think outside of the box of the system you're in. And so this is thinking of how numbers would be written in other ways of counting and which properties maintain. And I think that's very important. It's a recurring theme on our class, different bases. Because like I said, if we're both like thinking of surreal variations to our current system that could actually be better, and we like numbers, this is sort of on the mid-ground between that. So these are all interesting patterns, and another pattern we could ask that starts out quite base-dependent as well would be related to sums of digits. What happens when you add up the digits in a number? For example, we could note that in our base, if the digits in a number add up to a multiple of 9, the original number was a multiple of 9. And you get a similar property for 3. If the digits in a number add up to something 3even, a multiple of 3, the number itself is 3even. Now, is that because base 10 is magical? No, that's because 9 is the number 1 less than the base number, and 3 is a factor of that. And so it turns out you get similar powers in other bases for the number 1 less than the base number, and potentially for factors of that number. And you do get a superpower for the base number itself, which is it's the one that generates zeros at the end of stuff and is extra easy to spot multiples of. And other superpowers, like the factors of the base number, will have the easy trait that evens and multiples of 5 have in our base. So a lot of divisibility traits will be these pure things that are true in any of these bases, as long as you adjust your caliber from talking about 9 and 10 to talking about b minus 1 and b for one of these. Also, as a quick clarification, we are starting on base 2 on this chart. That's where they started it, like I would have. Although many people often mention base 1, and when people mention base 1, they often use the digit 1. And we have to note that that wouldn't be following the same rules as this. All of these bases are using a digit symbol for the numbers between 0 and 1 less than the base number. Or in other words, they're using the base number's amount of digits, but including 0. And the base number itself is the reset. So if you made a base 1 that tried to match this, it would be only using the digit 0, and it wouldn't actually be able to express different things. Also, if your spots in a number are powers of 1, then they don't have different amounts than each other, and you could have stuck your digit wherever, whichever place you want, and it still should have just meant a power of 1. And so tally marks are not actually the same type of base 1 that binary is base 2. You'd have to add some extra words in your name to say that you're using a different type of base. You can make something like that with other things called bijective bases or stuff. But if we're talking about these typical bases following at least the rule that you're including a 0 and your amount of symbols are your base number, no base 1s in the house. Base 2 is where it starts. And that's why in some of the traits in the Pandigital episode, I was like, extra emphasized for all positional base, or for all regular bases 2 and higher, or integer bases 2 and higher, because I've talked about a lot of weird bases on my channels, and some of those may have the same traits as the traits I mentioned, but there were parts of the episode where I was like, this applies to all bases. And so I had to be clear, by all, I mean, I've confirmed it applies to all of these bases and the further numbers that are integers 2 or greater. So these are the first realm of our extension of what a base could be. Then you can go outside integers, outside positive numbers, outside various ways, like we've done in episodes on my main channel. And you also could completely abandon the idea of being a positional base with powers of a base number. But even within that realm, we can see there's a lot of cool patterns. So the next thing we're going to ask about digit sums is going to be which numbers are divisible by the sum of their digits. Now, we said that the multiples of 9 were in our base. Actually, no, that's not necessarily true, because although the multiples of 9 have a digit sum that is a multiple of 9, you could have a number that couldn't divide the specific larger than 9 multiple of 9 that was its digit sum. If we asked if they could divide the digital root, which is taking the digit sum down to a single number, then any number could, to divide the digital root, your multiple of 3 can divide their digital root, a multiple of 9 can divide their digital root. But we're talking about digit sums. Which numbers are divisible by the sum of their digits? Now, on a trivial sense, we're going to say one-digit numbers can do that. They can divide themselves. Going forward, we can see in our base, 10 is divisible by 1, 11's not divisible by 2, 12 is divisible by 3. Next few are not divisible by their sum, and we get 18 is divisible by 9. That one, 20 is divisible by 2, 21 is divisible by 3. And so, which ones are divisible by their digit sum? Well, there's a name for that. It's often called Harshad numbers. It actually has other numbers as well, but here's some other names for it. Like many things in math, they got a bunch of numbers. We'll call them Harshad numbers for now. And here they're noting, they say that this article's under construction, don't rely on the info, but I read through this real quick and it seems that valid. Now, going through here, I really love this site, the OEIS, so I'm trusting them, even though they say they're under construction. Luckily, there's also a trait we can sort of verify ourselves on an individual number scale. We can see that we can test them. Now, it looks like maybe these are actually... Are these written in the base or written in base 10? That's not super clear, which we could look into that. But looking here on our table, we can see that if we were in another base, let's say base 6, well, this number represents 8 of a thing. And we're just using base 10 as our reference because that'll help us understand it. And it's not divisible by 3. This number 10 of a thing is divisible by 1 plus 4. So we get some interesting, and of course 6 is divisible by 1 plus 0. The 1-digit ones are divisible by themselves and stuff in the base. But which numbers have that property? Well, let's see also on Wikipedia has a bunch of information about this. And of course, Wikipedia pretty much always could have that warning. This is under construction, don't fully trust this, but they're pretty good for math, actually. And, you know, they're not flawless, don't quote them in your paper. But they give you the seed of the info, so you're able to know some fun stuff to look up and research or try out later. So here's, for example, the list of ones in base 10. Now, there's a random example. Here they're noting an example of what I said, that you might be tempted to generalize that all numbers divisible by 9 have this property, but 99 is a multiple of 9, but it's not divisible by the sum of its digits, 18. It would be divisible by the root of the digits if we added it down to 1 digit. And so here's one I mentioned in a short that's super trippy. Factorials look like they all do this. They look like all factorials are divisible by the sum of their digits in our base, but not all factorials do that. 432 factorial doesn't. And as I mentioned in my episode about factorials on my main channel, that made me look up a list that I put in there of what's the first factorial that breaks the pattern in different bases. And it turns out that some bases have a lowish factorial that isn't divisible by its digit sum, and other ones, they all are until some massive number, like 432 factorial. And this one just barely doesn't, because look, its digit sum has a prime factorization of 3 squared times 433. 432 could obviously divide the 3 squared part of it, but can't divide 433. It's one number too big for the factorial. It just misses. So they also note some other things, like here's some base 12 ones and stuff. And here's an interesting one that I also made a short about a while ago. You cannot have 21 consecutive integers in our base that all do that. You need any string of numbers in the base to eventually you're going to hit one that's not divisible by the sum of its digits in our base. And here's like the first run of a bunch of them. Here's estimating something called the natural density that was mentioned in my new episode. If they're talking about natural density, I have to read that because there's a few types of density. And various fun facts. Now, an interesting one on here that is true, don't worry about the under construction part of their page here. An interesting fact here is something says only 1, 2, 4, and 6 are Harshad numbers in every integer base greater than 1. And I've seen these called all Harshad, like all / Harshad numbers, or dash or whatever, something. And that means that they're this Harshad number divisible by their digit sum when written in any base. Now, that sounds crazy to be like any base out of the infinite possible amount of these. But, and as usual, they're saying integer base greater than 1, like I was clarifying for my stuff. When you look at a number, if I was wondering if 10 can have this property, well, 10 is going to be written with a single digit symbol, base 11 and upward. And that single digit symbol, in a trivial way, is divisible by the sum of its digits, which is itself. So as soon as you get up to past the base number, then you're good to go. Even the base number, you're good to go, because the base number will be written 10 in its own base, and that adds to 1, and it'll be divisible by 1. And then in further bases, it'll be a single digit symbol that will be divisible by itself. So to have this property, you'd only need to be divisible by your digit sum in all the bases smaller than you. But 10 isn't. If we look at 10, it's divisible by 1, it's divisible by 1 plus 1, but it's not divisible by 1 plus 2. So it's not going to work. And we're going to see a lot of these are going to have trouble doing that. However, if you look at 1, very trivially has that property. 2, in a pretty trivial way, has the property. It's 2 in all the other bases, except for here it's 1, 0, which adds to 1 plus 0 is 1. It's divisible by that. 3 in a slightly, or no, 3 doesn't do it. 1, 1 there, not divisible by 2. But 4 does do it in a slightly less trivial way, because we have it's divisible by 1 plus 0 plus 0, and 1 plus 1, and 1 plus 0. And there it is, itself. So it's divisible on all the ones leading up to it. And now it turns out there's only one other number in the universe it's been proven that does that, apart from 1, 2, and 4. And it is our magical number 6. Not only is 6 a triangular number, and not only is 6 the only triangular number that is also a factorial apart from 1, not only is it the only triangular number, this is a fact I still need to look up the proof for, but I read this once, so I believe it's the only the only triangular number whose square is a different triangular number. It's a perfect number. In fact, it's the smallest number known as a perfect number, because it's the smallest number who all of its divisors apart from itself add up to exactly itself. It is so many other names of property. It is a superior, highly composite number, and many cool titles. Well, it turns out it's also the largest all-Harshad number. The largest number divisible by its digit sum in every integer base 2 or greater. And once you get up to the single digits, we know it'll pass, but we know that 1 plus 0 will pass on the base number. But it has to get 2 through 5 correct, and it does. 1 plus 1, 2. It's divisible by that. 2. It's divisible by that. 1 plus 2 is 3. It's divisible by that. 1 plus 1 is 2. It's divisible by that. 1 plus 0, and we're good to go. So 6 is the largest all-Harshad number, because it's actually been proven that no larger numbers are going to be able to do that. So that's another property of our majestic number 6. Base 6 here also has a lot of amazing stuff we'll cover next grade. In grade -1, we did a lot of episodes about crazy bases. So in grade -2, we'll have at least a few bases, or a few episodes about more practical bases, such as base 6, such as balanced ternary, and some other ones. So I just want to get to the number 6. the number 6 just to see a list of more of the stuff it is. So it's a perfect number related to the Mersenne prime. It's the only even perfect number with that property. It is the root of this thing called an aliquot tree there. It is something called a perfect ruler. In addition, separately to it being a perfect number, it is a congruent number. It is the smallest, what's called a Granville number. It is a unitary perfect number, a primary pseudo-perfect number, a harmonic divisor number, and the last superior highly composite number to be also a primorial. So, and here we go, the largest of the 4 all Harshad numbers. And it's the amount of faces on one of the Platonic solid shapes. It is the amount of edges on one of the 2D shapes, one of the only 3 shapes that can tile the plane. Also happens to be an octahedral number. Every prime is one, apart from the numbers 2 and 3, which are its factors, is one less or one greater than a multiple of 6. It is what we call a pronic number, which is sort of like an almost square number in a way. It is so much stuff. So, I have learned throughout this grade. I didn't even know it as much as I know now at the beginning of the grade, but now I know. 6 is the most underrated number, and we'll probably continue to see it, as well as multiples of it. So, back to our base chart, we can note if we can ever convert to base 6, which is extra neat, and for all the base 12 fans out there, base 6 actually does all of your good stuff in a neater way. So we can see that we only get the digits 1 through 5, and here it just looks like they're climbing up there, because that's how they're going to look there. But when we see multiplication tables and fraction tables, we can see how superior it is. So that's a pretty fun one. Which numbers are divisible by their digit sum? Of course, we could ask other questions. Which numbers are divisible by their product of their digits? Which numbers is their product of their digits equal to the sum of their digits? Which would be verging on another interesting question we might cover later. We could ask all sorts of questions that might relate to having to be dependent on a base. And the key word there is that we are doing something with the digits. But even when we are stuck in a base and we see a trait like that, it might be a seed of a clue of a pattern that would exist on a whole infinite amount of possible ways of counting numbers. So, by the way, for people who enjoy this topic, I'm going to go to the combo class YouTube channel real quick just to show, even though everyone loves this bonus channel because of the shorts and the live streams and stuff, remember that my most thorough dives into topics that I'm most proud of are on this main combo class channel. And here's the new episode I put out 19 hours ago that make sure you watch that after the stream. Super crazy stuff about Pandigital numbers that this stream only scratches the surface of in comparison to the episode. But some other episodes apart from that that are related to these strange base topics are, obviously there's 3 that are about how to count in weird bases. That's in their name. And those are about what happens when you go to a really weird base. So like base 2i and other complex or imaginary, all these weird fractional and irrational bases or negative bases. So that's sort of a little trio that are about more obscure types of positional base, what number you're taking the powers of being a weirder thing. But there's also some episodes I've made that are just about a single topic and end up going down a rabbit hole of what happens with that topic in other bases. And that happens to a degree whenever the topic starts out being a base-dependent topic. For example, we're not going to need to talk about other bases much in an episode about prime numbers, necessarily. I mean, it could come up, but maybe less often because prime numbers are base-independent. The patterns I mention with them would probably be the same, just with a quick translation if we were in a different base, not different answers like some patterns would have. And one of the first episodes I made is magical properties of the number 9. That's when I spray painted 9 on the side of the house and ranted about 9s and started off the first non-intro episode of the show. And in that one, I do turn into an equation about what these traits about 9's divisibility means in other bases. And then a little bit later, here there's one about hyperelevens, of course. That one is, I would definitely watch that, and to a degree, the prequel to that is this 13 special types of numbers with strange names, because those ones, to a degree, this is also a prequel to that. These are sort of like a little trio. The hyperelevens is about those numbers that are all ones in different bases, but also these palindromic numbers went down the rabbit hole of different bases. So I also recommend the palindromic numbers for different base heads. And yes, we can, if we need to name these type of numbers that have properties in different bases, if we find something cool, we can call them something like hyper-based numbers. So, and for people who use the term based as slang, just remember where it originated from. Lil B, the base god. A very strange, innovative rapper and creative soul. So, as long as you remember the origins, it's a good word to use. Now, that's most of the crazy base ones, apart from the ones that are titled about different bases. And then the new one, of course. Now, in the new one, it's not just about fun facts about Pandigital numbers, but it's also about crazy paradoxical things you encounter when you try and compare or analyze larger stretches of number line approaching into comments. And thank you for joining me. Let's see how long we've been going for. It has been... Uh-oh, what happened? Oh no. What's going on? Sorry, my internet's being super weird. Hopefully it'll work. I need to sometime figure out why my internet gets weird sometimes. So, hopefully I'm coming through it all. Thank you all to everyone who stays around even when glitchiness occurs. I think we are good to go now, though. Now, on this stream, since we've been going for a while, I'm not going to go a crazy amount more of time. So people can feel free now, if they want, to leave any other questions they have, either about these strange bases or in general. I will be investigating more of these as time goes on, so strange bases will be a recurring concept, although, of course, in between that, I'm going to need to use base 10 to communicate it all in an understandable way. And let's see what else we have coming soon. So, I'm still pretty busy this month with private teaching and stuff, but I think that starting next month, I'm going to cut back on a lot of my private students and have more time to focus on combo class, as well as some writing projects and physical therapy and stuff I have to do because I got a bunch of surgeries last year. So hopefully that'll give me time to, for next month in March, have a clearer streaming schedule of which days I will be streaming. I also will be, like I mentioned last stream, sometime before March, opening a P.O. box here in California for people to send their old broken clocks, as well as if you have any dice. And they will be things that may get destroyed, but will probably end up in the background of an episode and gain a historic role instead of getting dust on a shelf somewhere. So I'll definitely let you guys know in a stream and or short or something when I have the address for that sometime before March. So take a peek out around your house, around your storage, your attic and basement and whatever. Got any clocks that are just collecting dust that aren't helping you out? They do have to be analog looking clocks. They can't be digital clocks. They have to look like a clock. But if you got any laying around collecting dust, you know who to send them to in a month. So, in addition to that, in March, I will be also working more schedule-wise with a few of my camera people. One of the main camera guys, Carlo, as well as a guy, Johnny, who I've filmed some of the episodes with, to work on the remaining 5 episodes of Grade -1, to finish most of those in February and early March, although they will be released throughout February and March, so that in March I can transition toward Grade -2, which will require me getting a haircut, getting a new desk, throwing away or destroying somehow a bunch of things, getting a bunch of new classroom supplies restocked, and other things that may be a surprise until then. Maybe I'll have to use this new thing I got, which is glow-in-the-dark spray paint. So that'll be pretty fun. Maybe we'll have to put some of that up in the classroom for Grade -2. And maybe you won't even know right away when it's up until it starts getting dark. And the remaining episodes on the channel will be about a week to a week and a half apart from each other. A few of them will be just around 10 or 15 minutes, but a few of them will also be really long ones, like the Pandigital one was, because some of them are topics that I've been planning all grade, hesitated to make because I wanted to make sure I got them correct and as good as I could get them. And now that we're near the end of the grade, it's time to turn them into something. And I'm not even sure exactly for 1 or 2 of the episode slots that I have remaining, because we're going for 36 episodes, which is in base 10. I mean, it's in base 10, it's 30, it looks like 36. But in base 6, it looks like 100. And hey, look, it's palindromic in base 5. Hey, look, it's also a rep digit, not a rep unit, but rep digit in that base. So we're going for, and it has zeros in a bunch of bases because it's a divisible number. We're going for that many episodes, 100 in base 6, the number we know is 36, or how all of these bases might write it in different ways. And that leaves 5 more episodes on the channel, and that includes a finale that will be more behind the scenes-y and include some rare footage throughout the grade that was never released, and will be really long probably. So part of what I will be doing in March is putting together a crazy finale in addition to resetting for next grade. As far as February, the episodes will be normal, maybe some of them more like a week and a half apart from each other, instead of a lot of the time it's been like a week or less. Some of these are now going to be maybe, like 8 or 10 days apart, so I can get them extra cool and extra good. And a few of them are just more silly, playful topics, like one of them that I need to fit in the grade just because it's time to fit in is one that's a mix of language and writing. It's sort of another language episode, which I did a few before, which usually end up being roasts of language, but this one's about spelling numbers. And so it ends up almost like when we look for traits in different bases, being similar of we're going to look at English and see some crazy surprising traits about how numbers are spelled and written, and using letters, and we could, guess about or figure out traits that might be necessary for any way of a language writing numbers. Sort of like we could use base 10 to get clues about what traits other bases might have if we wrote numbers using digits. It'll be like that, but using letters instead almost. Also reminds me of how I like using alliteration in some titles, like Pandigital, Paradox, and like ones with the same beginning letter. That's something that, only happens to be like a language-dependent trait for it to work. But, if you're stuck in a base, might as well enjoy your base-dependent patterns. If you're stuck in a language, might as well enjoy some alliteration. So, hello to everyone here saying hi. And someone's wondering if there's anything cool about the number 2008. And I believe there probably is. I don't know anything off the top of my head, but one thing that we can do if we're ever curious about a number is to either see if they happen to have a section for it on the Wikipedia article for the smallest round number under it. So they'll have a Wikipedia article for 2000, for example, and we could see if 2008 happens to get a mention there when they list some bonus numbers. And we also could look on the OEIS, the Online Encyclopedia of Integer Sequences, and there analyze, does this show up in any interesting sequences? So let's take a peek on that OEIS and see if 2008 shows up, and we'll also search it here on Wikipedia. But let's start by seeing if it's in any sequences. And hello to Brian McLogan there. Good to have you. And we got 2008. And that was searching in the Wikipedia sector of it. So we got to go to the home page, actually. So just to the OEIS. And we're going to see what 2008 shows up in. And some of these may be the facts that Wikipedia gives us in a minute as well, if they have any, but it's kind of fun to see it in context. So this is kind of a random one that must have been important for some particular problem. It is a number such that twice it, or 2 to the power of it, plus 3 is prime. A little random. Here we got one that it is the only number in quite a big range of this trait. And this is a very arbitrary one. It's about years. I'm almost surprised they put that on here. This is interesting. Number of 4x4 matrices with non-negative integer entries and row and column sums equal to 4, I guess. Unless, what's the offset here? Let's see. Equal to 3. So there are exactly, apparently, 2008 4x4 matrices with non-negative integer entries and row and column sums equal to 3. Someone's noting number of 4x4 stochastic matrices of integers. And we can also now look on if Wikipedia has any other ones. These are some other fun ones. If you started your Fibonacci sequence with 1, then 8, then played with similar rules, you'd get it. Okay, so now seeing if Wikipedia has anything fun, we are going to look at if they just have the calendar year, then we got to go for 2000. And no, I don't mean the year, I mean the number. And here, 2008. Oh, that's the one they mentioned. They mentioned the one that I thought was coolest. They also thought was coolest. It's the number of that I just said. So, to people who have other, I'm guessing that's like a birthday or an important year to you. To other folks who have birthdays in this range, which my birthday is a little before that, it's in the 90s. But here you get traits for most of them. You know, you get your sphenic number year. That's a number whose prime signature is 1, 1, 1. Or in other words, a number that's made up of 3 distinct primes multiplied together. 2002 is palindromic in our base. And then you get some other ones. Now, maybe we'll look at that more in the future for some of the past years. Looking at some of the years that are coming up, I am pretty excited about the fact that next year, although it is arbitrary now that our calendar calls it that year, you know, other calendars don't call it that year, stuck within this Gregorian calendar system, 2024 will be a tetrahedral number. That's when you add up all the triangular numbers, like the triangular numbers are the sum of the natural numbers. And like you could say the natural numbers are a sum of a row of ones. So we can find cool things about all sorts of numbers here. And that is even a fun game that we've played before that we'll play in the future, is picking a number range and trying to find the least interesting number in that range. And least interesting is highly subjective, but we would, learn some fun things while playing that sillier game. Sometimes if your silly game is using important tools or concepts, you end up stumbling into some important truths or questions anyway. So, when that tetrahedral year comes, we are going to make a giant tetrahedron, like you see this rotating tetrahedron there. Well, the tetrahedron we're going to need is going to need to have a height or amount of layers of 22. So that's pretty big. I'm going to need to buy sometime, this will be in late grade -2, or during this year, if I do it at the beginning of this year, it'll probably be during grade -2. If I wait until grade -3, that'll still probably be some point in this year. I'm going to need to get 2024 marbles and a ton of glue or something, because I want to make a tetrahedron for the year. So, thank you all for joining me again. I am going to log off pretty soon because this stream is just going to be about an hour. I may post a short or a bonus video later today as well. But remember that on the main channel, for those who haven't seen, that new episode about Pandigital numbers is one of my favorite ones I've put out. It is the longest one on the main channel, and I'm pretty, trying to be pretty concise with my editing and phrasing on those episodes compared to in these streams where I'm a little more free form. And so the length of the episode isn't usually on the main channel, just that I was ranting a bunch. If it's a longer episode, it means there was more subtopics I felt obligated to put in. And of course, I'm going to give my obligatory of the stream extra thanks to my Patreon supporters, and a recommendation that other people check that out if they want to see various bonus content, including a pretty long scene that got cut from the Pandigital episode that I'll be editing just to put on the Patreon in a day or two, which will be the core or seed of a future episode topic. But that's some of the stuff I put on there is bonus extra stuff that gives hints of the future or past, as well as thanking people in descriptions, and as well as I'll put the soundtracks of a bunch of the episodes on there soon. So thank you to all my supporters there, and thank you just to all of my viewers who comment on stuff and watch stuff. In the latest Pandigital episode, one extra fun thing to look out for is there are 3 squirrel cameos. Got very lucky when filming that. Normally in an episode, you're lucky if you get 1 squirrel cameo back there. They run by a bunch, but they do it so quick. All the time. We're there and a squirrel runs by on the fence, and I'm like, start filming. And it's too late. But this time we were already rolling, and I was already talking about stuff for 3 different squirrel cameos. So that's fun. Part of why I like having an outdoor classroom is those squirrel cameos, as well as the bird song. And despite the fact that the rain right now, which, let me check how it's looking out here. The rain's probably taking some of the clocks to their final stage. Alright, not too much rain, but we are sprinkling, so we cannot take any sort of field trip out there. Small chance we'll do a bonus video or something out there when there's a little break from the rain. In any case, I'm going to work on some writing in a little bit. Like I've mentioned in last stream and some other streams, I'm trying to, as I transition to spending more time as combo class, hopefully being my job and so on, part of that, although it won't detract from the videos because I will still have more time to make the videos than ever, part of it is also writing things that I want to publish, and eventually a lot of them may be free online, or I might sell paper copies of them. or things like that, but I just want them to be read. And some of the ones I'm working on right now are a very surreal fiction story and a book about threvens and throds, as well as a number of other projects that I get usually more carried away in my brainstorms, and I'm better at coming up with ideas than finishing the projects. I'm a little perfectionist about my books for some reason compared to my videos, but that's something I'm going to work on a bit today. So I will be, during part of that time, culminating some more fun facts about threven and throd numbers. And since one of the facts I'm going to take notes about, I remember seeing a good chart of in one of the books I have here about number theory. I might grab my number theory books for a moment to show you one of the things from there. And thank you so much to Quinn for taking down some notes about when stuff happened in a timestamp. If you can copy that to post like on the stream later, or I'll also screenshot it here now too. But if you can post it in a comment after the stream post, that'll be extra helpful, even if it's not fully complete. And like I've mentioned before, if people ever want to help out like with that, like Quinn's doing, of taking notes of when stuff happened, that's very helpful for future viewers. And I will like pin your comments or whatever to make it extra helpful for future viewers or viewers who missed part of the stream to click around to whatever topic they liked. And taking a look at one little number theory book right here briefly before I close off the stream, because I want to revisit this chart to take some notes on myself, and I might as well show it to you folks first. Although, to note, in the future, I may at some point do like writing streams where you guys can watch my process of researching and brainstorming and writing, but that's for another day. I've already promised a type of stream of me showing how to make digital beats that I never ended up being able to get around to. That I will do that one before long. That'll be fun, showing you guys how to make a beat from scratch. Now, out of all these awesome number theory books, which I'm now going to make full screen. One moment. With all these awesome books, one of them that I've been especially liking is this one, Recreations in the Theory of Numbers, packed with interesting facts and stuff. And this book got mildly rained on. Oh, that's bad. You hear this? Okay, no, now it's good, but the pages were acting kind of weird. You hear these? That's not a good sound for a book. Yeah, these all got mildly rained on. But I think they got dry enough that they won't grow mold or anything. So who cares if they're a little warped? They get the job done. Now, where is this thing I'm going to look for? Now, if we're looking at things like triangular numbers, or the family that triangular numbers and square numbers are in, called polygonal numbers, which are the numbers that, there are multiple ways of defining them algebraically, but in a sense, they're the numbers that if you made that amount of dots, it can be arranged in that shape, following, certain rules for how the dots have to be placed. And jumping to some of the things they have here about our polygonal numbers, they had some very interesting charts in here that reminded me of some cool traits about threven numbers, as well as some cool traits about square numbers. And we often think about square numbers as being, oh, you get them by taking x times x. That's x squared. But square numbers can also be seen as just the four-sided variety of what are called polygonal numbers, such as these polygonal numbers. And if we look at the equation for polygonal numbers and how many dots would be in one, the generalized equation here is pretty complicated. There's one way of writing the generalized equation. But what happens when I plug into that generalized equation, which has one variable for how many sides we want, like the n-gon numbered on a pentagonal would be 5, hexagonal would be 6, and the other for which level I want, how many stages into it I want. Well, when I plug in 4-sided for the level I want, which is square numbers, that crazy wacky formula right here, let me see where we're freezing. Oh no, sorry, yeah. N squared can be seen just as the square being lucky. Oh shoot, we're freezing again. Okay, the stream will be ending soon. Sorry for the freezing, but sorry about the glitchiness in the last couple minutes here. So, assuming this is still hopefully going, the square sort of just got lucky that this crazy formula that I'll show in a clearer form in a full episode before long simplifies when you plug in 4 to it. It goes down to r squared here. The triangular numbers got a little less lucky. Their formula simplifies to r times r plus 1 all over 2. So we'll go into this in a future episode, that there's a weird way that the squares just got lucky with their equation simplifying to something times itself. So you can sort of approach from a backwards way why squares are that. And there's many ways of defining what a square number is that we will go into later. And the thing about the revens I wanted to note here is that here's the chart that's showing 4 these different types of number, 4 different levels of them, how many dots are in a certain thing. Well, we'll notice that on the first level, they all just have 1 dot. On the next level, they have the amount of dots as like not level into it, but what level downward we're on. Which, if we're like a 5-gon, which is a pentagon, then it'll have 5 for that second level. And then in the third one, let's see what happens. 3 there, 6 there, 9 there, 12 there, 15, 18, 21. It's the threeven numbers amount of dots on the third cell. And at first you might be like, well, that doesn't sound that interesting. You got the threeven numbers because it was the third rank. But that's not true for any of the others. Even numbers are not the second rank. Natural numbers, all of the natural numbers 3 and above, or 2 and above if you counted these linear numbers or point numbers or 1, you could try and start it there too. All these natural numbers are the second level. A series of 1s is the first level. And from here, threeven numbers being the third level are the only some multiple of something 1 that happens in such a clear way. Level 4 is not just the multiples of 4. It goes 4, then 10, then 16, then 22, then 28. They're 6 apart from each other, but starting with 4, or 10, starting with 10, depending how you look at it. And so all the others here, it looks like we go 5, 15, 25, 35. For the 5th level, they're going up by 10 in each time, but they don't start on 10, so it's not the pure multiples of it. And so you have weird jumpiness on the other ones if you had to figure them out. But on the third level of each, it's just the pure threevens. Not what I actually know, it's just the threevens. I'm not going to say pure because I actually sometimes use the word pure threevens as a nickname to mean numbers who only have 3s in their prime factorization or are powers of 3. But we get solely the threevens in that column. And so that's a place where threeven numbers show up that evens don't. So threevens don't always just show up after you've already analyzed evens having a cool trait. Sometimes the threeven numbers show up on their own regard. and they have shown up in many episode topics, similar to how hyperelevens keep popping up, factorials and triangular numbers keep popping up, 3-evens keep popping up. And so that's something I'll be taking some notes about in my writings today, is some ways of putting that in the context of other things. And it will show up in an episode before too long, because there will be multiple episodes in grade -2, probably a whole little separated mini series of them that will be about polygonal and polyhedral numbers, and in general what are known as figurate numbers that are like that. A lot of interesting patterns there, similar to this tetrahedral number sequence that was on the screen before, and similar to what's really going on in those charts visually. So thank you all, and whoever said they barely understand but still said thanks. That's okay. I like when people who don't understand the videos watch them too. I think it's still good for your brain. I sometimes try and digest content that I find trustworthy and fun that I don't fully understand. For example, there are some mathematical papers I try and read that are above the level I understand, that are just really deep into some field or another's language. And I think it's still good for my brain. And when I was first getting into math, I remember watching a bunch of videos on channels like 3 Blue 1 Brown and Mathologer that I didn't fully understand. And now going back, I love watching the videos and understanding them and thinking that it probably actually helped me to have also watched them at that stage where I didn't fully grasp them, even if just to get the idea that that concept existed in the back of my head's language or possible future inventory. So you're all awesome. Thanks for joining me. Love you all so much, and I'm going to log off here to work on some random things. I will maybe catch you later in some stream or bonus video or short. If it's not later today, it will be within a day or two, because I love doing stuff on this channel. And also, just make sure you've all seen that full Pandigital episode on the main channel. It is the longest one yet, but it has a whole arc and a lot of fun facts. So, catch you all next time. Have a great day, and I'll see you soon. And sometimes it takes me a second to log off, so sometimes you get a little bonus moment.